Okay, so now we're doing some magnetism questions. Okay, so first one. An electromagnet is made by winding wire around an iron core. The diagram shows an electromagnet connected to a circuit. State two ways of making the strength of the electromagnet weaker. Okay, weaker. So we can reduce the number of coils. Okay, that's one way. Or we simply could reduce the power or voltage of the battery. Okay, it's two ways, and it works the opposite. So basically, if we increase the number of coils, we can make it a stronger electromagnet. If we increase the voltage of the battery, we can make it a stronger one. Okay, next question. Explain why the core is made of iron instead of steel. Okay, once the switch is open, okay, meaning it's like that, and no current is flowing through the wires, the iron core loses its magnetism. Okay? Whereas steel will stay magnetized. Okay, so that's the difference. Okay, so both can be magnetized, however steel will stay magnetized. Okay, a question could be, why do you use iron instead of wood? Well, in that case, iron is more iron, nickel or cobalt are the three elements in the periodic table that can be magnetized, so therefore any one of them is useful to use. Iron is used commonly because it's commonly found in the earth, in iron ore. Okay, so those are two questions. However, what is magnetism? So if you've ever heard of the word electromagnetism, okay, you can immediately see the word electro, okay, could mean electricity or electron, and then you've got the word magnetism as the second half of the word. Okay, so basically electricity and magnetism are linked, so that's the reason why we've got this word. Okay, now loads of scientists in the past obviously made important discoveries. Michael Faraday, okay, James Clerk Maxwell was another famous scientist that sort of helped with putting forth the theory of electromagnetism, or the idea of electromagnetism, forward. And some of the ideas they came up with was essentially that if we've got a wire like this and we've got a current flowing like that, okay, it could be conventional current or electrons basically. Now if you take your right hand, okay, and go like this, we call this the screwdriver rule. Your thumb is going to be the direction that the current flows, and your fingers that wrap around it like that are going to be the direction of the magnetic field that is caused as a result of movement of current. So if I've got my circuit like this connected to a battery or cell, okay, and if you notice there's a gap, okay, there's a very slight gap there. If I connect up the cells properly, and now current actually flows around this wire, we are going to get, according to the right hand rule, a magnetic field, okay, that, okay, is shaped like this. Okay, so it's 90 degrees. Notice it's 90 degrees. My fingers are 90 degrees to the direction of motion, but they go in a coil. Sorry, they rotate like this. Okay, so actually you got a magnetic field going around the wire like that. Okay, So that's what we call the right-hand screwdriver rule, okay, and it's important for questions later on, okay. But why is it important? Basically, it tells us that an electric current, okay, a movement of charged particles always is accompanied by a magnetic field like this, okay. Now, the other important thing in electromagnetism, okay, is basically how the first question we were talking about electromagnets, okay? So let's say this is our iron core, okay? Let's say we've dug it up from the ground, we've purified it, okay? Here's a slab of iron, we've shaped it into this nice rectangular shape. Now, obviously, nobody has created a small machine that we can shrink ourselves and then we can actually go inside the atoms and see what actually is happening, okay? But for GCSE purposes, okay, all you need to know is, and we identify them like little arrows like this. Basically, there are three types of metals, okay, cobalt, nickel or iron, that can be magnetized, okay, in their pure states. Now, when you dig them up from the ground, these little things here, which we have called, scientists have called these things, called domains, okay? These are sort of like mini magnets, okay? Or they have like little magnetic fields around them, okay? However, generally, more often than not, these are in a random order, okay? Sometimes they might be, you know, in some regular order in some parts of it, and that's why actually some iron ores are actually magnetic when you dig them up from the ground, okay, and you don't actually have to pass electricity through them. However, sometimes they're not, okay, and in actual fact, we can actually increase the strength of this iron ore now by actually passing an electric current through a piece of wire that's wrapped around it, okay? Now, if I put my wire around like this, okay, coil it up like that, like our first question had, okay, connect it up to a battery, pass an electric current through it, what's going to happen is, and I'm not going to draw the wire anymore, or in this diagram, basically, the domains, or mini magnets, are going to line up like this, okay? So these are called domains. Now, there's sort of many north-south poles like this, many north-south poles. Now, basically the overall effect of this is that this magnet becomes, you get a huge N on this side and a huge N on that side, okay? And then the magnetic field lines go like that, okay? North to south, okay? Now, I've only drawn two field lines here, okay, going from the north to the south pole of this magnet. But, actually, what do these field lines tell us? The closer they are together, the stronger the magnetic field. The further away you are from the magnet, or either of the poles, the strength of the magnetic field actually decreases, okay? So, it's sort of like gravity. In fact, it's very much similar to gravity. So, you can imagine S is the black hole, or north is the black hole. Okay, the closer you get to the black hole, the stronger the gravitational pull is, okay? Or the closer we come to Earth or the Sun, the stronger the gravitational pull the Earth or the Sun has on that particular object, okay? It's the same in electromagnetism or magnetism, okay? So that's what field lines are. And hopefully you know from primary school that a north pole and a south pole attract, and a north repel, or a south and a south repel, okay? So those are basic rules that you need to know, okay? And it's just revision at GCSE physics, okay? But now you know how magnets are formed, okay? So these would be steel magnets, and once they've been magnetized with a wire, all those domains are lined up, okay? You actually can demagnetize some magnets. Sometimes if you actually bang it hard enough on a hard surface, you can cause these domains to go back to their random order, okay? But again, the wonderful thing about electromagnets is that once the current is off, the magnetic field decreases, and basically the magnetism, the magnet becomes less strong, and you can use it in useful circuits. And basically, I'm going to show in a later video how these can be used. Okay, but these are the basic ideas. So we're going to do Fleming's left-hand rule now. Okay, so Fleming's left-hand rule. Okay, and how, why is this important, and where is it used? Okay, so basically the idea is, again, here's my wire, here's my current. Okay, it's going from left to right. Now, if I have a north pole magnet there, and if I have a south pole magnet here, and my magnetic field, okay, is gonna go from north to south, like that. Okay, that's just the way how a magnetic field works. Now, Fleming's left-hand rule states that if we have a flow of charge, okay, in the presence of a magnetic field, that flow of charge is going to experience a force. Okay, and the rule is basically you need to use your left hand. Okay, and let me go through what each finger represents. Here's your thumb. This is going to represent the motion, the direction of motion that the current will take. Okay, sorry, yes, not of the current, of the actual wire. Okay, so let me explain, and it'll become clearer in an example. Then your first finger, or your index finger, I'm gonna say first finger because I'll show you in a second why, is gonna be the direction of the magnetic field. Okay, F for field. Then your second finger, not your mid, it is your middle finger, but I'm gonna call it the second finger because the C in that one is gonna be the direction of current. Okay, so if I write this down, so my thumb, do a large M for the motion of the wire. First finger, F's for magnetic field, then second finger for current. Okay, so yes, this is magnetic field, and this is the motion of wire. So we come back to this question, or this example. We have our field, which is the first finger, going downwards. Okay, do you see that? My second finger is this one, and notice it's going that way. Okay, meaning my thumb is actually pointing into the piece of paper. So it's actually going in to the piece of paper. And how do we denote that? Okay, it's like the back end of an arrow. Okay, let's say it's in to the paper, and that's so that means if this was the actual wire, it would actually fall through a piece of paper. Okay, the force would actually push it down that way. Okay. Change of example, I'm now going to keep the magnetic orientation the same, however, the current is going the opposite direction. Okay, so I'll just draw the magnetic fields for you. Okay, north to south always. Now, left hand. North to south is down, current is my second finger, and notice where the thumb, it's pointing towards the camera, okay, out of the piece of paper towards you. Okay, and how do we denote that? We denote it by a dot, which signifies the tip of an arrow, as if the arrow is pointing towards you. Okay, so into the paper is the end, the feathers of the arrow, the cross sign, and then if it's coming out of the piece of paper, it's a dot pointing towards you. Okay, the tip of the arrow. So it's out of paper. Okay. So again, pause the video, make sure you're comfortable with doing these sorts of examples. So that means, in this case, if that was the wire, it would go up. Okay? So that is Fleming's left-hand rule. Where is it used? Well, it's used in electric motors, because if you think about it, what is an electric motor? Well, it's essentially electricity or some sort of electrical power device, source, causing movement. That's what motors do. So, I draw basic motor for you. So here's my north end, south end, south up. If you think about it, north to south is like that. Our current is going into the piece of paper in this particular case, because remember I said we're placing our circuit in between the north and the south pole. So let's use our rule. So north to south is our field, okay? Our second finger is the direction of the current. Well, that is going into the piece of paper. I know on the piece of paper it's drawn as if it's going upwards, but imagine that's going into the piece of paper. Field north to south, current is going into the piece of paper, and what does it mean for the thumb? Well, the thumb is pointing downwards. So actually, this end of the wire is actually going to flip down this way, okay? So this current it should have an arrow like that, okay? Because it's actually going into the piece of paper. Right, let's do the other end. So north to south, that hasn't changed. But this time, the arrow, I know it says it's going down, but actually that means it's going up. If you think 3D, okay? So the current is actually going towards you. Which direction is the thumb? It's pointing upwards. So it means this end of the wire, okay, is actually going to be pushed upwards. What do you notice about the arrows? They're in opposite directions. How does a motor work? It rotates. So that's going to push upwards, this is going to push downwards, so it's going to rotate around like that. Okay? And basically as the circuit flips, as the coil of wire flips, okay, the commutators don't change, but the current maintains this orientation. So every time it flips, this end of the wire is always going to go into the paper. This end of the wire is always going to come out of the piece of paper. Okay, so just to clarify, look, current's going in towards you, and then when it goes down, current is going down, okay? And it goes in a circuit like this. So current is going towards you, down, towards you and down, okay? So that is Fleming's left-hand rule, okay? And that's its application. That's how an electric motor works, and that's how we get that rotational movement, okay? So that's Fleming's left-hand rule. Okay, so we're going to do Fleming's right-hand rule now and apply it to a generator. Okay, so basically the same thing, exactly the same thing, except we're using our right hand, and also make sure 90 degrees between every finger, like I've got there, okay? So, what is a generator? Basically, in every power plant, okay, you've got some sort of rotational movement, okay? And that can come from a windmill, okay? So we've got a windmill rotating, or it could come from some water that's been heated up from heating up or burning coal, oil or gas, okay? Or from a fission reactor, okay, basically, and the high pressurized steam will rotate some turbines which will be connected to a generator, okay? So let me explain what I've got here. So the first bit is the rotational movement from the steam or the wind, Now, that is connected to a coil of wire in between two magnets. North magnet, south pole magnet. Okay, so, and if you see the rotation is going around like that, okay, so that means this section of the wire, or the coil of wire, is going to go up, and this section of the wire is going to go down, okay? So the motion of the wire is in orange, and the direction of the field is in purple. So with my right hand, that's the field. Motion in this particular case, it on the left hand side is up. So my current is going to go into the piece of paper, or the arrow is shown like that. Okay, that's going into the piece of paper, it's going that way. Okay, if I do it the other way, north to south, thumb is going like that. Thumb is going downwards, and I point towards you. Okay, so current is coming out of the piece of paper. Okay, now what is it showing us? So if we follow this through, current goes down here, okay, through this bit of wire. Now this is connected to one end of the ammeter, okay, and then it passes through the ammeter and goes around, completes the circuit, and for a split second, or just a few seconds, we've got a complete circuit of current, okay? So it goes around like that, and like that, okay? And the ammeter reads +1 amps, okay? Now, obviously this bit of wire is rotating. So let's see what happens when we've moved it a quarter through its cycle. So I've drawn several diagrams. So this is the next stage that happens. So just to recap, we start off with this diagram, okay? Basically, the coil of wire is parallel to the magnets on either side. Now it's gone like that. So this time we don't get a force, because if you think, try with your right hand, your field and your motion are no longer 90 degrees. Okay, and when they're no longer 90 degrees, you can't apply Fleming's right hand rule. Okay, and basically you get no current being produced here. And if you notice, we get 0 amps. And if you look at the connectors, they actually don't connect up to the ammeter, or these commutators here. Okay, so that's why we get 0 amps. So we're now at a quarter of a stage through our cycle. Let's go halfway. So let's recap. First we start off like that, a quarter. Now we flipped over like that. Okay, so we're on here now. So basically the terminals, or the wire, these ends of the wires have flipped. But if we follow Fleming's right hand rule again, okay, north to south, and the motion is going up, denoted by the orange wire, it's going up. Okay, current goes into the piece of paper, that's the arrow there. If we do the opposite way, we've got north to south that way, thumb going down, current goes towards you, so we got current coming out of the piece of paper. Let's follow it through. Okay, so current goes around there. Okay, this time, notice from the first time, this wasn't connected, okay, but this time, now the current goes through here, goes down this bit of wire, connects to the bottom of the ammeter, goes through it, and passes through this wire, which goes through the rest of this circuit like that. Okay, so just again, goes down here through the ammeter, through this wire, and again through the circuit. So this time the ammeter reads -1. Okay, notice that's different to our original +1 there, okay, at the start. So basically we've got current going the opposite direction, okay, and we can begin to see the start of what we call alternating current. Okay, but let's just finish the cycle first. So we started off like this, gone like that, then like that, and the last bit is going to go like that. Okay, so here's my last bit, last diagram here. Okay, notice again the commutators these connectors do not connect to these commutators, to the connectors of the ammeter at all, so we get a 0 amps reading. Okay, and again if you look at the orientation of the wire with respect to the field, the motion is parallel to the field. So field, north to south, motion, our thumb is parallel, so we can't apply Fleming's right-hand rule. The motion needs to be 90 degrees in order for us to get a current induced, okay? So basically, that's why we get 0 amps there. So lastly, I've just drawn these two graphs here, or set of scales here. So basically this is the amps, or the current, and this is voltage. So, I start off with 1 amp at t equals 0. A quarter of the cycle, notice we get 0 amps. So basically, the waveform is going to look something like that. Okay, so we get a maximum positive amps. When we get to t over 2, what do we get? Halfway through the cycle, we get minus 1 amps. So I need to go down here. So basically, I'm going to go down there. What happens when we get 3/4 of the cycle? We get 0 amps. So I go back to, sorry, just make sure you can see that. I go back to 0. And to complete the circuit, we go back to our first picture, and we get plus 1 amps. So we've got one full cycle, and this is the pattern that we get. Okay, so this is what we call an alternating current waveform. Okay, and it's exactly the same as voltage. Okay, because if you think about what is voltage, it's the power or the energy per unit charge. So the amount of energy that is passed on to each electron to pass around the circuit. Okay, without voltage we don't have current. Okay, they're partners. Okay, shall we say? So basically it follows the same waveform. So when we have maximum current, we're going to have maximum voltage. Okay, when we get 0 current, we're going to get 0 voltage. Okay, when it's the other way around, the same. So it follows exactly the same wave pattern as the current. Okay, so this is what we call AC current, alternating current. Okay, I know it's a double negative. AC stands for current, so we actually don't need this word, but it just makes people say AC current. Okay, but strictly it's just AC. So we have alternating current, and that's the end of the lesson.